Good morning, everyone. A very good morning before the Independence Day. So we were discussing about the ultraviolet spectroscopy in the previous classes, and we have discussed up to the principle and the spectroscopy. Just I'm sharing. So we have discussed about the principle to magnetic spectrum, the visible spectrum, some natural organic pigments, instrumentation demonstration, and principle behind the UV visible spectrophotometers, right? So we know the UV visible spectrophotometer is such a type of instrument that are using for the detection of double bonds and the absorption and the concentration of the compound. Okay. So the instrument is depending on the Beer-Lambert law, where the formula for the Beer-Lambert law is like log 10 I0 by I, where I0 means the intensity of the light at the time of falling, and I is the intensity of the light at the transmittance. So the molar absorptibility is the absorbance of 1 mole of solution if it crossing 1 centimeter safe. Okay. So principle behind the UV spectrophotometer, just discussing like this way. Relative energies of various orbitals. We know that the electrons are revolving around different orbitals, okay, from the nucleus. So there are different type of bonding and anti-bonding cells are there. Okay. So from the lowest cell, that is the sigma bonding. Just 1 second, I'm just zooming it. Okay. See the sigma bonding, and from sigma bonding to pi bonding, and N means non-bonding, and pi star, that is the anti-bonding, sigma star anti-bonding. So these are the normally ground state, where the electrons are residing in the ground state. Okay. Next, they are going to from one cell to another cell and one orbital to another orbital. Okay. Now, whereas it represents the pi orbital, pi star, that is antibonding, and sigma star, this is antibonding. That means they are not bonded and they are the lone pair of electron. Okay. So these energy gaps are different in different compounds. Like the difference in energy between two orbitals. There will be some difference between the orbitals. So the delta E is represented is the energy difference. Planck nu. So whereas nu, there is a frequency, is whenever it is derived. So Planck's constant into c by lambda. C the velocity of the light, where if it is reciprocated, then frequency, that is the new lambda, new reciprocal is given. Okay, just invert it. Okay. So the when light passes through a compound, some of its energy promotes an electron from one of the bonding or non-bonding orbital to one of the anti-bonding orbital. That means the electron will be residing particularly about some the nucleus. So whenever light will be passed through that solution, electrons will be absorbing some of the energy. As a result, they will be crossing the orbitals from lower energy to higher energy state. Okay. So the electrons from one of the bonding or non-bonding orbitals to one of the anti-bonding orbitals. The frequency or wavelength of the absorption depends on the energy gaps between these two energy levels. So how the absorption will be depending between the energy level. That is from, you can see the steps here, from sigma to sigma star. It's a long gap. So from sigma to sigma star, it requires the maximum energy. But from sigma to pi or sigma to n, it's required the less energy. That means from pi to pi star, that is also. So if we make a ascending order or descending order, you can very clearly assume these bond energies. Okay. So speed of light is known as the c, and frequency here is the Greek letter nu. Okay. And lambda max, that is also wavelength. Okay. That you know from the higher secondary level, that is the speed of the light is depending, or the wavelength of any particular light, or any wavelength frequency of any light can be calculated through this formula. Okay. So electronic transition, you can see the structure here, energy transition from sigma to sigma star. You can see the higher the energy. Okay, so like from sigma to pi star, energy is lower, and like this way, pi to pi star and n to pi star and n to sigma star. The bonding energies are like this. The higher is the energy gap, the lower is the wavelength of the light absorbed. That means whenever the energy gap is higher, the lower is the wavelength of the light absorbed. That means whenever any light having a lower wavelength, the light will be absorbing lower wavelength. As a result, their energy will be higher. We know shorter wavelength compound or shorter wavelength light having a higher frequency. Okay, so bigger jumps require more energy, so absorb light with shorter wave. That means if shorter wavelength light is absorbed, then it is easy to jump from one energy to more energy. And if higher wavelengths are absorbed, then it will be revolving from lower frequency. So that means whenever any compound is in non-bonding state, if it want to go to the pi bond, then more amount of energy is required. As a result, it can absorb the higher amount of light, higher wave. That means some compound can be found with the lower wavelength, some compound can be found with the higher wavelength. That means whenever any compound shows their absorption in the lower wavelength, like the 200 near about this, that means the compound having little amount of double bond. That means their energy gap or the requirement of the energy is lower. So not electronic transitions are allowed. Certain restrictions should be considered for electronic transitions called the selection rules. So here you can see the spin quantum number of an electron should not change during the electronic transition. Means you can see delta sign, delta plus and delta minus. So the spin quantum number of an electron should not change during the electronic transition. Okay? And the transition between the two orbitals should be symmetry allowed. That means there is obviously some symmetry is following from which cell to another cell it will be going. Any transition that violates the rule will be forbidden. These are called forbidden transition. And the most common forbidden transition is N to pi star. Sometimes it has been found that some of the compound are absorbing very small amount of energy. So this type of compound is known as the forbidden transition. So that is generally found in the non-bonding to non-bonding N to pi star. Okay. So electronic transition in alkanes, you can unconjugated alkanes, see, you can see pi to pi star transition takes place around F170 to 190. So I have already discussed about that lower wavelength requires, if lower wavelength compound is there, that means they do not require higher energy. Absorption rate for conjugated alkenes like C13-butadiene having the 217 lambda max. Like this way, 1313 cyclohexadiene, cyclopentadiene, these compounds are increasing their lambda max inappropriate with the amount of dienes. In carbonolysis, N to pi star around 190 millimeter and N to pi star around 280 nanometer. Since N to pi star transition is symmetry forbidden transition, intensity of the transition is much lower than the other allowed transition. So other examples are there. See, for the C double bond, that is the ethene, the excitation is pi to pi star and maximum wavelength 160F and it is the solvent. Hexane can found this type of transition. Now, hexane, C triple bond. And this C triple bond 1 hexane, that is also found for the pi to pi star. and C double bond O, ethanol, and nitrogen. So this type of bonds are generally found in different phases of compound, and the transitions are here presented. Now convention and terminologies. So there are different terminologies associated with the UV vision spectroscopy that is very important, like the chromophore, bathochromic shift, and hyperchromic shift and hypochromic shift, like this way. So you should note down this or take a screenshot. Chromophore. Chromophore means a covalently unsaturated group responsible for electronic absorption. That means unsaturated group that is covalently attached and that is responsible for electronic absorption. Like C double bond O. They are the covalently compound, unsaturated, and their saturation will be like this, the hydrogen. That is a chromophore. That means some of the compounds show different colors. If the color compounds are there, they are known as the functional group for the presence of color is known as a chromophore. So chromophore is what? Chromophores are the group which will be showing the colors. Functional groups which will be showing colors. So C double bond O, C double bond NO2, amides, esters, this compound show the visible wavelength. They can produce the color to the compound. Oxochrome. That is a saturated group with non-bonded electrons which when attached to a chromophore alters both the wavelength and the intensity of the absorption. Like OH, NH2, NR2, SH. Okay, that means a saturated group with non-bonded electrons are there. Whenever they will be attached with the chromophore, alters both the wavelength and the intensity of the object. Now, important is bathychromic shift, that is the shift of absorption to longer wavelength, also known as a red shift. Hypochromic shift, hyposochromic, the shift of absorption to shorter wavelength means the absorption will be shifted to shorter wavelength. Hyperchromic effect, an increase in absorption intensity. Hyperchromic effect, a decrease in absorption intensity. Okay. Next, we have solvents and solution. Next coming solvents and solution. These are the very important effect of solvent and effect of solution with the absorption. So that will be discussed in a practical also. So if we change the solvent or dissolve any particular compound with another solvent, their absorption maxima will be changed. C. Solvent should not absorb UV radiation within the same range as the substance. That means paracetamol is whenever solved in acetonitrile or chloroform. So if acetonitrile is used as a solvent, then their absorption maxima will be different. If it is dissolved in chloroform, then your absorption maxima will be different. So this compound particularly having this type of absorption maxima. That means whenever we are analyzed any paracetamol or anything you have found in your lab also, suppose paracetamol is dissolved in the water, and then we have to set the blank wavelength at the particular wavelength within the blank solution. Then with the paracetamol, whenever dissolved in any water, then we have to check the wavelength difference. If the solvent is changed from water to HCl or NaOH, then their wavelength will be changing. Okay. A strong absorbing solvent allows very little amount of light pass through the solvent. Means strong absorbing solvent allows very little amount of light. That means if the solvent absorbs a maximum amount of wavelength, as a result, what happens? It will allow less amount of light to pass through the sample because it is absorbing maximum amount of light, right? So we have to check such a particular solvent which will be absorbing minimum amount of wavelength. As a result, there will be chances to absorb the maximum amount of wavelength by the compound. As a result, we can detect their absorption and the concentration. Non-polar solvents do not form hydrogen bond with the solute, so fine structure is often observed. See the non-polar solvents. They do not form generally hydrogen bonds. As a result, fine absorption maximum, and polar solvents form solute-solvent complexes through hydrogen bonding. Hence, fine structure may disappear. That means sometimes some polar solvents are absorbing with the hydrogen bond with the different another compound. As a result, we cannot find the particular prominent peak. Okay, so selecting different compound absorption, we should select especially non-polar possible. Okay. Now solvent effects. That is one of the important. What are the effects? What are the parameters that are affecting in the UV visible spectroscopy? Like this solvent effect. The position and intensity of an absorption band may shift if the spectrum was recorded in different solvents. Conjugated dyeing in an aromatic hydrocarbon experience very less solvent effect, and alpha beta unsaturated carbonyls show different shapes in bands for the changing solvent from non-polar to polar protic pool. That means if any conjugated diene, if any compound contains conjugated diene, aromatic hydrocarbon experience very less solvent. Aromatic hydrocarbon like benzene, toluene, this compound uh, is not so much affected by the solvent because they are very rigid in their structure and they are not just bonding with another solvents like this one. So conjugated diene and aromatic hydrocarbon are very good. So they are not, their wavelengths are not too much changes by the solvents. Alpha beta unsaturated carbonyl compounds show two different shapes in bands for changing solvent from non-polar to polar protic one. That means if any compound alpha beta unsaturated carbonyl compounds are there, so if the solvent is changed from non-polar to polar protic solvent, proton generating solvent, then some of the shift will be shown. Like pi to pi star band moves to longer wavelength, n to pi star band moves to shorter wavelength. N orbitals get established due to more polarity by solution, then pi orbitals, n orbitals get stabilized mainly by hydrogen bond. Next, effect of conjugation, you can see there are different symbols are there where from one bonding to another bonding, effect of conjugation is found. And you see energy, ethylene, butadiene, less energy required, hexaquines, less energy. So molecule ethylene, it requires 165, but if the solvent is like higher, 1,3-butadiene, 1,5 hexatriene, or beta-carotene, they are having the higher maximum or the wavelength is higher. See, 470 beta-carotene is a colored compound that is visible in the above the UV range. So we should choose such an amount of solvent which are having lower absorption maxima than this. Okay. Next, effect of conjugation. Effect of S6 and S trans compounds. So you can see the lambda max for these two compound, whereas it has a cis configuration, it has a trans configuration. So in case of cis configuration, you can see the lambda max is higher, and in case of trans configuration, the lambda max is lower because the electrons are stabilized, and here electrons are not stabilized, they are repulsing each other, but this compound is stabilized. As a result, they are absorbing small wavelengths. Probably repulsion between the functional terminal lobes of the phi 2 increases energy of the in a cis form, and hence less energy is required for phi to phi 3 transition. Suppose we have taken one compound that is also having same configuration, cis type of one, but the functional group is different and they are placed in different places. Hmm. We're not saying that functional group different. Functional groups are same, but their positions are different. Cis and trans. Substitution will force a molecule to take a cis from and therefore absorb energy from a longer wavelength than under usual spectrum. So effect of conjugation you have studied. In cyclic system, a double bond is forced to say in cis cissoid form, therefore shows a red shift in the drops in intensity. Here is the example: homoannular, heteroannular. Homoannular means the lambda mix of this compound is lower than the heteroannular. And the heteroannular system is sometimes having lambda max more present the compound, the homoannular having triangle.